Hello, I am Sten Delos. I'm a postdoctoral fellow at the Max Planck Institute for Astrophysics, and I'm going to tell you about prompt cusp features that are expected to lie at the centers of dark matter halos in collisionless dark matter models. So let me start with some background. We know there's about 5 times more dark matter than baryons. Because of this, dark matter drives gravitational structure formation. That is to say, galaxies form inside collapsed dark matter halos. Here's a picture of what that looks like for our own Milky Way galaxy. So this is density as a function of radius for dark matter and for baryons. And this is plotted to scale, that was a simulated realization of the galactic disk. So the general picture here is that the halo is going to be much larger than the galactic disk itself. But this is not the whole story. Not all halos have galaxies. Dark matter halos form over a huge range of scales. Here's a simulation that covers that range. So at the largest scales, we see the cosmic web. Zoom in, we'd see halos associated with galaxy clusters. We could keep zooming in, we'd start to see halos associated with individual galaxies. If we keep zooming in, we'll eventually find halos that are at scales too small to host any baryons at all. So these halos be completely dark. We can keep zooming in. At the smallest scale, we'd see actually halos that are around Earth mass. Also, there are subhalos that can persist inside larger halos. Well, here's a picture of a simulation of this is actually a Milky Way scale dark matter halo. And all these points in here are subhalos. Now, a simple but useful way to describe a halo is with its spherically averaged density profile. So that's the density as a function of radius. The general picture here is that halos are dense toward the center and less dense farther out. Also, if you plot them logarithmically like this, you find that the decrease in density is shallow at small radii and steep farther out. Now, we find that density profiles of all halos turn out to be pretty similar, even at very different scales. So this picture is showing dwarf scale halos and cluster scale halos, and you see the same general trends in the density profile. In fact, this universality was confirmed over 20 orders of magnitude in halo mass. So this plot is, it's actually the slope of this plot, but the main point here is that each of these curves is considering halos in a different mass range, and they all overlap. Now, density profiles turn out to be universal, basically because despite these huge scale differences, all of these halos formed in essentially the same way. They grew from smaller halos. But what about the first halos? So these are not grown from smaller halos. They form directly from the collapse of peaks in the initial dark matter density field. So the idea is that in standard dark matter models, the initial density field would be smoothed by thermal motion. For cold dark matter, maybe on Earth's mass scales, it can vary a lot depending on the dark matter model. But what happens is that each local maximum in the resulting density field would collapse to form a halo. Now, this process is not normally resolved in simulations, but here is a movie of what it looks like. So here I'm showing the time in units of the collapse time. This is the characteristic size of the initial peak, which I'll get to later. But the basic picture here is that we have this density peak. It starts gradually becoming more dense until suddenly it collapses basically all at once to form a halo. Now here is the density profile of that halo. This is density as a function of radius for different times going from purple to red. And what we see here is that the density profile seems to settle into a straight line. That means in this logarithmic plot, a pure power law. So it already looks different from the universal density profile that we saw earlier. Also, if we can scale this plot, so we can instead plot density times radius to the 3/2 power as a function of radius, and it's a horizontal line. So that means that the density scales as radius to the minus 3/2 power And something that's really interesting about this is that this r to the minus 3/2 cusp forms and stabilizes almost immediately after the halo's formation. For this reason, Simon White came up with the name prompt cusp. So what happens to this halo's density profile over longer time scales? Well, so this is a plot of density times radius to the 3/2 against radius again. And as time goes on, going from purple to red, we see that there's a buildup of new material that increases the density profile at larger radii, eventually making something that looks like that universal density profile that we saw earlier. But the prompt cusp persists at the center. And there's similar behavior for other simulated halos. I should also note that this result should not come as a surprise. New material has too much energy and angular momentum to disturb the center of the system. That's why it's just settling at large radii and building up the density at large radii. Now, what determines the properties of prompt cusps? Well, there's a remarkably simple answer to that. Remember that the cusp is set immediately as the halo forms. Because of this, it can only be sensitive to the immediate neighborhood of the initial density peak, namely the height, the curvature, and the tidal field at the peak. So we can characterize an initial density peak by its characteristic size, which is set by the curvature, its collapse time, which is set by the height and the tidal field. And this leads to a prompt cusp with density coefficient, that's proportional to the density of the universe at the collapse time, times the physical size of the peak at the collapse time. The mass of the cusp is essentially the mass of the peak, and the radius of the cusp is essentially the proportional to the physical radius of the peak at the collapse time. And I should emphasize that everything except the numerical coefficients in these relationships are demanded by dimensional considerations. So these predictions work well for a sample of halos. So these are 12 halos from a variety of different power spectra, and I'm showing the density profiles going. So this is density times radius to the 3/2 power again as a function of radius, going from early times in purple to late times in red, and the predictions are these black lines which extend out to the predicted radius. And we see that the predictions match the red curves pretty well. So we connected prompt cusps to density peaks, but what's the distribution of density peaks in the first place? Well, actually, that's well understood. It was described nearly 40 years ago in this article. And here's a test we can do. So we can count every peak in an initial density field, plot the differential number density of peaks distributed in the predicted cusp coefficient, and then we can actually simulate that field and look at the cusp distribution that arises in the simulation, and two match pretty well. There is a tendency to find fewer halos than peaks. This is probably something like mergers, which would bring the overall number of halos down. Okay, so moving on, I've talked about how dark matter behaves gravitationally, but what is dark matter? Well, of course we don't know, but we can get guidance from the idea that dark matter must have been produced somehow. And one well-motivated idea is that dark matter is a thermal relic, so it's a particle with this kind of interaction with the standard model. And what can happen then is that the dark matter can be pair-produced, going in this direction, from standard model to dark matter, in the hot early universe. So that's the production mechanism, but that also implies that today the dark matter can annihilate into standard model particles, which we could detect. And moreover, that annihilation rate is proportional to the squared density, which means it's boosted by any kind of inhomogeneity, and in particular, it's going to be boosted by the high density inside prompt cusps. So more specifically, remember, we argued that every halo and subhalo, so I argue the prompt cusps survive, and therefore every halo and subhalo should have one at the center. Moreover, the extreme density the extreme density inside prompt cusps would boost the annihilation rate, and this boost is in some sense egalitarian because every halo, no matter its size, would have roughly the same prompt cusp. What that means is that if we're thinking of a galaxy scale halo, we don't really care about what's happening in its own prompt cusp, which, by the way, might be significantly disrupted by baryons, for example. But what really matters are the prompt cusps of all of its subhalos. So how much do prompt cusps boost the annihilation rate? Well, let's consider an example model. So this is let's think about a 100 GeV weakly interacting massive particle that kinetically decouples at 30 MeV. The result is only logarithmically sensitive to these choices, by the way. So an application of the statistics of peaks tells us that something like 20,000 sub-Earth mass prompt cusps should reside in every solar mass of dark matter. If we calculate the annihilation rate in these cusps, we find that annihilation in larger halos is boosted by factors ranging from around 30 for dwarf scale halos up to maybe 1,000 for cluster scale halos. So that's pretty large. Also, there's a change to the spatial distribution of annihilation in a halo because the signal from unresolved prompt cusps scales as the number density of cusps, which is more like, which would go something like the average dark matter density and not the density squared. So here is an example of what that means for the signal from our own galactic halo. So this is a plot of flux from dark matter annihilation as a function of angle from the galactic center. So the orange dashed line here is showing the signal from the smooth galactic halo. The green is the signal from galactic prompt cusps. This dotted line is the signal from extragalactic prompt cusps, and the blue is the total. So we see that actually in the center, so at the very center, like looking toward the galactic center, the annihilation signal is dominated by the smooth halo. But as we look farther out at our angles larger than maybe 20 degrees, the prompt cusps dominate. So the general picture here is that we don't expect an annihilation boost from prompt cusps in the very centers of galactic halos, but we should expect a large boost everywhere else. Actually, there's also an interesting implication that we can already draw from this plot, because these black dots are showing the measured excess of gamma rays from the galactic center in the 1 to 10 GeV range. So this is the galactic center gamma ray excess. It appears to be consistent with dark matter annihilation in the smooth halo, this orange curve. But if it is dark matter annihilation, then a significant signal is then also predicted at larger angles due to prompt cusps. And for comparison, here I'm showing the Fermi collaboration's measurement of the isotropic gamma ray background in this same 1 to 10 GeV range. So what this is telling us is that if we attribute the galactic center gamma ray excess to dark matter annihilation, then annihilation should also contribute a significant fraction, maybe 20%, of the measured isotropic gamma ray background in the same energy range. And that seems like a pretty small fraction, but I should note that the isotropic background is thought to mostly come from unresolved astrophysical sources, so there isn't much room to fit dark matter. Okay, so I've been talking about annihilating dark matter, but prompt cusps also have significant observational implications for another class of dark matter models, and that's warm dark matter. So in the warm dark matter paradigm, random particle motion smooths the initial conditions on particularly large scales. This is all happening before halo formation, but once halo forms, the usual picture is that the consequence of this is that you get fewer low mass halos. So if this was a cold dark matter Milky Way mass halo, this is what it looks like in warm dark matter. However, the initial peaks in this smoothed density field are much larger than those in the original density field, and that means the prompt cusps are going to be larger. So here is a plot of a simulated halo in a warm dark matter scenario, 3.5 keV. I'm showing the halo density profile at redshift 20 and redshift 4. And the dashed line here is the predicted prompt cusp, which, by the way, matches the one in the simulation quite well. And this dotted line is an inosto fit. So this is the fit of the universal density profile. So the density profile is not directly measurable. So let's look at something that is more close to observations. This is the circular orbit velocity as a function of radius. And the conclusion here is that below about 100 parsecs, the prompt cusp raises the circular orbit velocity compared to what you would conclude if you just extrapolated using the inosto profile. So we could constrain warm dark matter by searching for prompt cusp within nearby dwarf galaxies. So what this is showing is that the inferred density profiles of some of the classical dwarfs from this paper. So that's the black and the gray. And on top of that, I've plotted the 68% and 95% lower limit of the prompt cusp distribution. So what we can see here is that for 2 keV warm dark matter, that's probably that seems to be in tension with some of these halos. 3.5 keV, probably not so much. But this is kind of illustrating the general principle. I should note that better constraints come from ultra faint, but the plots don't look as nice, which is why I didn't show them here. Okay, so that's it. I'll just summarize the main point here. Gravitational collapse produces prompt r to the minus 1.5 cusps, which persist through halo growth. These features greatly impact dark matter annihilation. We now expect an annihilation signal not only from the densest regions, but from diffuse regions as well. And also, if the dark matter is warm, prompt cusps should affect galactic kinematics and maybe other observables as well. Thank you.